Hi everybody, and welcome to your very first Physics 100 lecture. Today we're going to be covering the material that you'll see in Chapter 1, a brief introduction to scientific reasoning. What I have here on the picture for you to look at is a very famous photograph taken during the beginning part of the 20th century. There's a gentleman sitting down here, a very famous one by the name of Nikola Tesla. And he took this picture to show for demonstration reasons how safe what we now call AC current or alternating current is for electrical systems. Here we have electrical bolts shooting across his laboratory while he's down here reading a book. These electrical bolts are at hundreds of thousands of volts, and the frequencies on his alternating circuit are in the hundreds of thousands, which is much higher than we even see today in our typical electrical equipment. But how did he know that he can turn that on, have that apparatus work, and he would be completely fine? Well, Nikola Tesla was an absolutely amazing individual in every stretch of the word. But the reason why is because not only because he was smart, but because he used reason. He understood the scientific principles behind electromagnetism, and he knew that if he was to arrange it in such a way that he would be completely fine. And in fact, you can see he's in this chamber, and he went on to have a very, very prosperous career. So what is science? Well, what science is, it's a body of knowledge. It's our understanding of the material world that we've acquired. It's not just numbers, but observations through history. It's an ongoing human activity. And of course, it has beginnings that precede recorded history. And you can see that we have this demonstrated, a body of knowledge. These are scientific journals down here. It's an ongoing activity. Here's a young scientist that's carrying out an experiment with electromagnetism. And of course, here's a manuscript, and I believe this one is written in Arabic, of a scientist who lived not in pre-recorded history, but he lived in, I believe, the 1200s. So this is something that's been going on for a long time. This is a handwritten manuscript that's probably been copied and handed down through the centuries. One of the important things we need to know about science is that science is dependent upon this concept of measuring things. If we have the ability to measure something, then we can say that we have data on that issue or on that fact. So measurements or data collection are a hallmark of good science. I put a quote here from Lord Kelvin to show you exactly how important scientific measurements are and why we conduct them the way that we do. By the way, Lord Kelvin didn't come up with the idea of scientific measurements. It goes all the way back to a guy named Aristotle, who understood the nature of science, probably for the first time, and then wrote about it. So Lord Kelvin, who lived during the 1800s, said, "I often say that when you can measure something and express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever it may be." And that is how science is. If you don't have hard numbers in a lot of cases, a lot of times it's really difficult to convey that information to others. We actually have this relationship amongst other people, right? If somebody says, "Listen, do I have enough money in my bank account to pay for it?" and the wife says, "We have enough," that might be satisfactory in the moment, but it doesn't really tell you exactly how much money is there and whether or not other things could be afforded, and it can convey some degree of discomfort between people. So numbers and science, the ability to measure and to get precision on things is important. You can notice that we have this word science right here. There's a little atom on top of it. But notice over here there's a beaker. And on the beaker are little measurement lines and then a thermostat down at the bottom. So these are typical, a ruler is a typical symbol of science. So what do we do with these measurements and why are they valuable? Well, measurements relate to how much you know about something, right? If you know, for example, if I asked how much was in my bank account, and somebody said, I think we could afford it, that's not very reassuring. So that doesn't mean that I have very good knowledge. And I certainly couldn't say that I have scientific knowledge of the amount that's in my bank account. The same thing is true of when you look at a tree and somebody says, how many leaves are on that tree? You can estimate maybe 1,000,000, 10,000, who knows, right? Depends on the tree, depends on how big it is, and it depends on how accurate we want to be when we measure this thing, okay? One thing that we can do, for example, is we could take small bits and get an idea of the overall nature of something. That's one of the great things about scientific measurements. For example, a pinhole image of the sun nicely leads to a calculation of the sun's diameter. This was something that was done in the 1800s, and they actually had a pretty good idea of how big the sun was as a consequence of simply taking a piece of cardboard, as is demonstrated right here in this picture, and letting that light filter in and measuring the diameter here and the distance here. That became a proportionality argument using simple 6th grade mathematics to calculate not only the diameter of the sun, but also to figure out something about what they believed to be the distance to the sun. And they were able to get a pretty accurate measurement of it as recently as about 200 years ago. Some people actually were accurate prior to that, but for different reasons. Okay. Here's another type of measurement that we could take. These are observational measurements. So these are round images of the sun or over here. But during a solar eclipse, of course, this is, in case, by the way, I probably should introduce this person in this photograph. Your textbook is written by a man by the name of Paul Hewitt. This is Paul Hewitt's wife. So we are using mainly his photographs in this first lecture. And so you can see she's cleverly demonstrating these nice round circles. But when the eclipse hits, those circles have turned into crescents. And the reason why is they're basically mirroring what we see here, right, as the sun moves along. So we're actually seeing an image of the sun being projected onto the ground. This is an important observation that we could make. So mathematics is the language of science. Integration of science and mathematics occurred some 4 centuries ago. I would say probably the first one to really do that was a guy named Galileo, but the guy that you're always going to hear named for doing that is Newton, who came just right behind him. Newton was an amazing human being. He had the ability to see things that most other people couldn't. Not only did he come up with one law of physics, he actually came up with 3 laws of physics just in motion alone. He also got involved with thermodynamics and the way that things cooled and the way things heated up. And then, just for fun, he invented calculus on the side to prove his theories right. So the guy is an absolute genius. And this is the part that will maybe you'll hopefully remember a little bit more, is that not only did he write all these wonderful treatises on physics and the physical universe and the nature of things, especially in motion, but he actually spent 2/3 of his writing about church-related things. Nobody ever reads those anymore. They're more interested in the science. But that just shows how brilliant this man is that he could write all of these wonderful things that would take most people 3 or 4 lifetimes that turned out to only be 1/3 of his writing. Amazing individual. The other beauty of math is that it allows us to be able to condense very complicated things to a very simple expression, right? Force equals mass times acceleration. That's a difficult thing to say in words, and people weren't able to do it until Newton actually sat down and had it done. Ideas of science are unambiguous when expressed in mathematical terms. 2 + 2 = 4. That's unambiguous. You can't make that fuzzy in any way, shape, or form. Equations of science provide expressions of relationships between concepts. Okay, just as I gave an example, force equals mass times acceleration. It's a very straightforward expression that does express that relationship. And of course, equations are guides to thinking. I put some examples here. This is out of a university cafe. Actually, math and science are cool. They are really cool. And here's some fun clip art. I put this over here to show you that some people really get into their math. Don't worry, we're not going to be doing anything remotely like this over on the side, but it doesn't mean that the equations aren't kind of pretty to look at from time to time. If you were to major in physics, though, you would learn a lot of the mathematics that you see in this picture over here to the side. Okay, scientific methods. In general, scientific methods refer to principles and procedures for the systematic pursuit of knowledge involving 1, recognition and formulation of a problem. This is important. You have to recognize what it is that you want to study, what it is that the problem is, and have that in your mind the entire time. You don't want that to move or shift on you. You'd find that a lot of people will get data and try to make their question match their data. You can't do that. You actually have to have the question right up front. 2, the collection of data through observation and experiment. So after you've got your question or you've formulated what your problem is, go out and start looking at the things, start measuring things. For example, you might be interested in, say, the way that Kilauea erupts lava onto the lava field. What are the kinds of observations you can make? Well, you can go out and you can measure the temperature of the lava coming out. You can measure the color of the lava that is coming out of Kilauea. You could come out and measure the volume of lava that is coming out of Kilauea. You can make observations about the kinds of rocks and minerals that are forming as a result of the crystallization of these lavas coming out of Kilauea. So it's a lot of really interesting stuff you can do. Okay. Step number 3, the formulation and testing of hypotheses. Right. So the hypotheses is, what is it you think is bringing this about? Okay, and then going out and testing that. And one of the best ways of doing that is trying to prove yourself wrong, right? If you can prove yourself wrong, then you know that you can reject that hypothesis, and it's better that you throw away your own hypothesis before somebody else proves you wrong and you look foolish, right? And of course, I just want to show, right? This is an old World War II poster that's been rewritten with science on it, showing that, I mean, I have to admit, when I was at UCLA, most of the scientists now in the halls in the geology and physics programs were female, which I think is kind of a neat and exciting thing. Maybe science needs some new perspective and some fresh blood in there, actually looking at some of these problems we've been stuck on for many, many years. Albert says, the case is never closed. Many experiments may prove me right, but just as I just said, but it takes only one to prove me wrong. And he's absolutely right about that. If your hypothesis doesn't hold up to a test, we got to reject it and move on to the next hypothesis. That doesn't mean that the problem doesn't still stay and that the data isn't good. It just means that we don't understand what it all means. So those are the scientific methods. Now, you'll find considerable dispute in, I would say, in political realms, as well as in between academians, even amongst themselves, as to what the scientific attitude should be, right? We just talked about what the scientific method is, but the scientific attitude is a little different. And so let's go ahead and read through this, because I think this is a very effective list that is actually reflected in your textbook. The scientific attitude is one of inquiry, experimentation. Well, first of all, let's talk about inquiry. I don't want to get ahead of myself. Inquiry means asking questions. Experimentation means going out and measuring things and figuring out whether or not the nature of your inquiry is valid. And then willingness to admit error. Hey, we're all human, and we all make mistakes. This is a big problem, actually, among some scientists. I've been in meetings where they just, despite the fact they have data thrown their way showing that they're wrong, they will not admit the error. So you want to be able to have the right attitude towards these things, which is to say, if you have new data that I don't have that shows that I might be wrong, I want to hear it so that I can change my hypothesis and get a better and more accurate understanding of the phenomenon I am exploring. So scientists, 1, are experts at changing their minds. Yes, they absolutely are. And they have to be willing to occasionally bite their pride. 2, must accept experimental findings, which is to say test for erroneous beliefs and understand objects and positions of skeptics. This is another thing that is in the scientific attitude that I think needs to be enhanced, is that, for example, if we were to tell the public that global warming is going to cause problems A, B, and C, and we have a whole population of people that think that global warming is not true, then we need to understand their objections and understand the positions that they have, so that we can approach it from a perspective, or approach it from the direction that would best help them if in fact the data shows them to be incorrect. Just as an example. Test for erroneous beliefs. This is extremely important. You'll find that there are a lot of beliefs for example, physics for a long time believed that in outer space that it wasn't a vacuum, that there was this cosmic fabric that existed that they called the ether, through which waves could travel. We'll talk about the ether a little bit later in the class, about halfway through the class. It's a really kind of interesting idea. But that's been shown to be erroneous. So it had to be rejected. But it didn't mean that it died easily. It took a long time for people to kind of reject it. Okay, again, the scientific attitude. Fact is a close agreement by competent observers who make a series of observations about the same phenomenon. And a scientific hypothesis is an educated guess that is only presumed to be factual until supported by experiment. Right? A lot of times these things are, people will say, I have a theory about this, but they've tested nothing. So they really don't have a theory, they have a hypothesis. Right? But a fact is a really cool thing. Right? A fact is a fact, and it's a fact no matter when it is a fact. It's one of the only things that we can call truth in science, because everything else is really an interpretation. At least in the early stages of your careers, you'll find that to be so. So a fact is something that if I go out and I measure a stick and it happens to be 4 inches long, okay? If that stick is 4 inches long, it doesn't matter if in 100 years that stick will still be 4 inches long unless I've destroyed the stick. But in that time and place, it was still 4 inches. And it will always be a fact. And as a matter of scientific inquiry, it's not unusual for people today to go and open up old journals from the 1850s and 1860s and look at their data, their facts, and then reinterpret them to today's understanding of the sciences. Okay? So a nice little cartoon over here. Facts are revisable data about the world. Theories interpret facts. That's absolutely right. Again, the scientific attitude continues. Law or principle. So we need to know what these things are. A law or principle is a hypothesis that has been tested repeatedly and it has not been contradicted. Nice little law of gravity strictly enforced here. Of course, it's thank goodness that the law of gravity is strictly enforced on planet Earth or we'd fly into space. But a hypothesis that has been tested repeatedly and has not been contradicted, that means it's never been found to be wrong. That doesn't mean it's right, though. You can be right for the wrong reasons. We just simply haven't discovered what that is. And this law or principle, which is to say it's been tested repeatedly, has not been contradicted, is based upon something called the induction fallacy in science. And those of you that study logic or have an interest in reading about logic or Aristotle will come across this notion of the induction fallacy. So the idea is imagine you live in a world where all you've ever seen are red apples. And so you start to write books and you start saying all apples are red. And of course, one day somebody hands you a green one and you look like a total fool. But up until that time, all apples are red until demonstrated to be different. As a matter of fact, you can go on Wikipedia and you can read about the so-called black swan, which is one of the scientific notions people used to say all the time. All swans are white until European explorers went to Western Australia and found flocks of black swans. And so these became known as black swan events, things that are unexpected because society had accepted long ago that something is fact, when in fact it wasn't. There are exceptions. So laws or principles can in fact be shown over time to be incorrect. I have several other examples, even recently in geology, what we now call the plate tectonic theory. It's only been around since the 1970s. Prior to that, there was another theory, and people just would not let that one go either because it was just made too much sense, and it couldn't be contradicted, in their opinion. So down here we see a theory is a synthesis of a large body of information that encompasses well-tested and verified hypotheses about certain aspects of the natural world. Okay? So theories are these wide synthesis, this idea that kind of tries to tie everything together into a single framework in which all these other things spring out of. Okay? Science and technology. Science is concerned with gathering and organizing knowledge. Technology is the use or the application of scientific knowledge for practical purposes and to provide tools for further exploration. And of course, we can see this for medical research right here. And then I took this as a screenshot from the, I believe this is Terminator 1, or it could be Terminator 2, the 1990s apocalyptic film. So let's get back to the basics here. Physics is the basic science, right? There are many different sciences now. As a matter of fact, the original scientists that looked at the world were called naturalists. They looked at physics, they looked at rocks, they looked at biology, but they've since all separated themselves off into sub-disciplines. For example, the physical sciences include geology, astronomy, chemistry, and physics. Here we can see this beautiful mountain range where the rocks have actually been folded on end due to tectonic processes. Astronomy, here we actually see, and I believe this is the Andromeda Galaxy, spiraling around at an extremely high rate, but it's so large that it looks like it's not moving at all. It's fascinating stuff. Life sciences include biology, zoology, and botany, right? Here we see the double helix, a poor model, but there's a double helix anyways to indicate DNA. And then, of course, we see this bird being born. And then physics, of course, underlies all the sciences, right? Physics is the study of the matter and the energy that goes into all of these things. Without an understanding of physics, there is no biology or zoology or botany. At least it's not comprehensible to us. Chemistry doesn't make sense to us. Geology doesn't make sense to us. So as a consequence, physics is where it all starts. And that's where we're going to start our class. So if you have any questions, feel free to send me an email. We'll go ahead and open up the chat discussion. So if you have any questions there, please chat away over on the Einstein Cafe, and we'll see you in the next lecture. Thank you.